You have never seen your home. Not really. Not from the outside. You have lived your entire existence inside a structure so vast that light itself needs 100,000 years to cross it, and you have never once stepped back to take in the view. The Milky Way, that soft, luminous river arching across summer skies, is not a river at all. It is the edge of a disk, the edge of a spiral, the edge of something that, when seen from above, would reveal a secret that astronomers kept hidden from themselves for most of human history. At the heart of our galaxy, cutting across its center like a cosmic blade, lies a bar of stars so enormous that its very existence rewrites our understanding of where we live. This is not a small feature. This is not a minor architectural quirk. The Milky Way's central bar contains billions of ancient suns, stretches across tens of thousands of light years, and rotates through space with such gravitational authority that it has shaped the destiny of every star in the galaxy, including our own. And we did not even know it was there until 20 years ago. For centuries, we assumed our galaxy was a simple spiral, an elegant pinwheel of stars spinning in the cosmic void. The images were beautiful, symmetrical, orderly. They appeared in textbooks and planetarium shows, on posters in astronomy classrooms, and desktop wallpapers on computers around the world. But those images were wrong. The truth is messier, more interesting, and far more difficult to see. Imagine trying to understand the shape of a forest while standing deep inside it. You can see the trees immediately around you. You can look up and see patches of sky through the canopy, but you cannot see whether the forest is circular or rectangular, whether it has clearings in the middle or extends uniformly to the horizon. You are trapped inside your subject. This is precisely our predicament with the Milky Way. We are embedded within its disk, roughly 27,000 light years from the galactic center, positioned in what astronomers call the Orion Arm, a relatively minor spiral structure between the galaxy's major arms. From this vantage point, we see the galaxy edge on, compressed into that familiar band of diffuse light that ancient Greeks imagined as spilled milk. But there is another problem, one far more sinister than mere geometry. Between us and the galactic center lies an ocean of dust. Not the dust you sweep from under your bed, but microscopic particles of carbon, silicon, and ice that absorb visible light with merciless efficiency. Look toward Sagittarius on a summer night, toward the very heart of the Milky Way, and you are seeing less than 5% of the way to the center. The rest is hidden behind a curtain of darkness that no optical telescope can penetrate. For most of the 20th century, this curtain remained closed. Astronomers could study the edges of the galaxy, map its outer spiral arms with radio telescopes, and make educated guesses about what lay at the center. But guesses, they remained. Then came infrared astronomy, and everything changed. Heat-sensing telescopes see the universe differently, while visible light bounces uselessly off dust particles. Infrared radiation slips through. Longer wavelengths, lower energies, patient photons that have learned to navigate the cosmic haze. In the 1980s and 1990s, infrared surveys began to pierce the veil toward the galactic center, revealing tantalizing hints of structure that no one had anticipated. The hints became certainties in August 2005. NASA's Spitzer space telescope, a heat-seeking eye floating in the cold void beyond Earth's atmosphere, had been methodically surveying the plane of the Milky Way as part of a project called GLIMPSE, the Galactic Legacy Infrared Mid-Plane Survey Extraordinaire. The name was ambitious. So were the results. When astronomers at the University of Wisconsin analyzed the data, they found something extraordinary. The density of infrared sources, essentially the number of stars, was not distributed symmetrically around the galactic center. One side was noticeably denser than the other. The asymmetry was not subtle. It screamed from the data with the clarity of a neon sign. Robert Benjamin, the astronomer who led the analysis, put it simply: they had found the bar. Not just any bar. A bar roughly 27,000 light-years long, about 7,000 light-years longer than previous estimates had suggested. A bar tilted at approximately 45 degrees to our line of sight, which explained why one side appeared denser than the other. A bar composed of old red stars, ancient suns that had been orbiting the galactic center since before our own sun existed. Ed Churchwell, a professor of astronomy who had worked on the GLIMPSE project, captured the magnitude of the discovery. This was the best evidence ever for a long, central bar in our galaxy. A feature this dominant had been hidden for as long as humans had studied the stars. The Milky Way was not a simple spiral at all. It was a barred spiral, a galaxy with an elongated rectangular core of stars cutting across its center before the spiral arms began their outward sweep. We had been living inside one of the most common types of galaxies in the universe without even knowing it. What exactly is a galactic bar? Think of it as a cosmic traffic jam frozen in time and stretched across tens of thousands of light years. In a barred spiral galaxy, the stars near the center do not orbit in perfect circles. Instead, their orbits have been elongated, stretched into ellipses that align with one another. When billions of these elongated orbits overlap and pile together, they create a dense linear structure, a bar of stars that appears to cut through the galaxy's core. But the bar is not stationary. It rotates. The entire structure wheels through space like a cosmic propeller, completing one revolution roughly every 220 million years. This rotation rate, what astronomers call the pattern speed, is one of the most fundamental properties of the bar, determining where its gravitational influence is strongest and where it fades into the broader galactic disk. Recent measurements, including groundbreaking work using data from the European Space Agency's Gaia spacecraft, combined with infrared observations from ground-based telescopes, have pinned down this pattern speed with unprecedented precision. The bar rotates at approximately 33 to 40 kilometers per second per kiloparsec, a technical unit that essentially measures how fast the bar sweeps through space as a function of distance from the galactic center. These numbers may seem abstract, but their implications are profound. At this rotation rate, the bar's corrotation radius, the distance from the galactic center where stars orbit at the same speed as the bar itself, lies roughly 6 to 7 kiloparsecs from the center, or about 20,000 to 23,000 light years. Beyond this radius, stars orbit faster than the bar rotates. Inside it, they orbit more slowly. This creates resonances, regions where the gravitational influence of the bar pumps energy into stellar orbits, pushing stars onto new trajectories and sculpting the structure of the entire galaxy. The outer Lindblad resonance, where the bar's gravitational pull is particularly effective at perturbing stellar orbits, lies just beyond the solar radius, uncomfortably close to our own cosmic neighborhood. This means we live in a region of the galaxy directly shaped by the bar's influence. Our Sun does not simply orbit the galactic center in isolation. It dances to the tune of a structure that most humans alive today have never heard of. The scale of the bar is difficult to comprehend. Current best estimates place its half-length, the distance from the galactic center to one end of the bar, at approximately 5 kiloparsecs, or about 16,000 light-years. The full bar, end to end, spans roughly 10 kiloparsecs, or 32,000 light-years. For comparison, the entire disk of the Milky Way is only about 100,000 light-years across. The bar represents a significant fraction of the galaxy's total extent, but length is only one dimension. The bar also has thickness. Unlike the razor-thin disk of the spiral arms, the bar puffs outward above and below the galactic plane. This vertical extension becomes particularly dramatic near the bar's center, where it connects to the bulge, the dense, football-shaped concentration of old stars surrounding the galactic core. In 2016, astronomers using data from NASA's Wide Field Infrared Survey Explorer WISE mission produced an image that made this structure visible in a way that no previous observation had achieved. Melissa Ness, a researcher at the Max Planck Institute for Astronomy, and Dustin Lang, an astronomer at the University of Toronto, applied image processing techniques to WISE data and revealed something startling. The Milky Way's bulge was not just boxy or peanut-shaped, as previous studies had suggested. It was X-shaped. The X shape is unmistakable in their images, two diagonal streaks of stellar density crossing at the galactic center, like the letter carved into the heart of the galaxy. This structure, technically called a boxy peanut bulge, is not unique to the Milky Way. It appears in many barred spiral galaxies when viewed edge-on, but seeing it in our own galaxy, confirmed beyond doubt by direct observation, was something new. The X-shape forms through a process called bar buckling. As the bar grows and accumulates mass, gravitational instabilities cause it to bend out of the galactic plane, warping vertically in a dramatic buckling event. Stars that were once orbiting in a flat disk suddenly find themselves on trajectories that carry them high above and below the galactic midplane. Over time, these orbits stabilize into the characteristic X or peanut shape. Computer simulations predict that this buckling occurs within the first few billion years of a bar's existence. The Milky Way's bar, based on the prominence of its X-shaped bulge, likely formed long ago, perhaps 8 to 10 billion years in the past, when the galaxy was still settling into its current structure. How many stars are in the bar? No one knows precisely. The Milky Way contains somewhere between 100 billion and 400 billion stars in total, a range of uncertainty that would be embarrassing in almost any other field of science, but is unavoidable when counting dim, distant objects through veils of cosmic dust. The bar and bulge together account for a substantial fraction of this total, perhaps 20 to 30% of the galaxy's stellar mass. This means the bar alone contains tens of billions of stars. Each one is a sun. Each one has been burning for billions of years. Many have planets. Some of those planets might have atmospheres. A tiny fraction might have life. The numbers cascade outward into realms of pure speculation, but the foundation is solid. The bar is not empty. It is crowded beyond imagination. The stellar density near the galactic center, the heart of the bar and bulge, reaches almost incomprehensible levels. Within 1 parsec of the supermassive black hole Sagittarius A, there are approximately 10 million stars. That is 10 million suns crammed into a volume just 3.26 light-years across, a space so dense that the night sky from a planet in that region would blaze with stellar light, the concept of darkness rendered meaningless. These stars are predominantly old. The bar is dominated by red giants, ancient suns that have exhausted the hydrogen in their cores and swelled to enormous sizes, their surfaces cooling to a ruddy orange glow. These are population 11 stars, metal-rich objects that formed from gas that had already been enriched by generations of earlier stellar deaths. They are the grandchildren and great-grandchildren of the galaxy's first stars, carrying in their atmospheres the chemical fingerprints of billions of years of cosmic evolution. Some studies suggest the bar contains two distinct populations of stars with different scale heights, different degrees of vertical puffiness above the galactic plane. One component, roughly 180 parsecs thick, resembles the old thin disk near the Sun. Another, even thinner component, at around 45 parsecs, appears predominantly toward the bar's ends. These nested structures hint at a complex formation history, multiple epochs of star formation, and perhaps multiple phases of bar evolution. At the exact center of the bar, at the precise core of the galaxy, sits the object that makes all other structures seem modest. Sagittarius AR, a supermassive black hole with a mass of approximately 4 million suns. This is not a small black hole. Stellar mass black holes, formed from the deaths of individual massive stars, typically contain between 5 and 30 solar masses. Sagittarius A is hundreds of thousands of times more massive. Its event horizon, the boundary beyond which nothing can escape, spans about 12 million kilometers, comparable to the diameter of Mercury's orbit around our Sun. Light that crosses this boundary is lost forever, adding imperceptibly to the black hole's mass. In May 2022, the Event Horizon Telescope, a planet-spanning network of radio observatories working together as a single Earth-sized telescope, released the first image of Sagittarius A. The picture shows a bright ring of superheated gas surrounding a dark central shadow. The ring is not the black hole itself, but rather the accretion disk, material spiraling inward, heated to millions of degrees by friction and gravitational compression. The shadow is the black hole's silhouette, a region where light has been captured and cannot escape. The image confirmed what astronomers had deduced from decades of indirect evidence. Sagittarius A is real, it is massive, and it sits at the exact dynamical center of the Milky Way. Stars orbited at speeds exceeding 10,000 kilometers per second. Gas falls toward it in chaotic spirals, and yet, compared to black holes at the centers of other galaxies, Sagittarius A is remarkably quiet. Most of the time, our galaxy's central black hole is dormant. It does not produce the brilliant jets of energy seen in active galactic nuclei. It does not outshine its host galaxy. It simply sits, patient and dark, occasionally swallowing a cloud of gas or an unlucky star that wanders too close. Recent observations suggest that Sagittarius A experienced a significant outburst approximately 200 years ago, a flare of X-rays that lit up nearby molecular clouds before fading back into quiescence. On cosmic timescales, this was moments ago. The black hole is not dead. It is merely sleeping. The bar did not always exist. In the early universe, the Milky Way was a chaotic assembly of gas clouds and proto-galactic fragments, colliding and merging in the gravitational maelstrom that followed the Big Bang. The thick disk of our galaxy began forming approximately 13 billion years ago. just 800 million years after the universe itself came into being. At that time, there was no bar, no spiral arms, no recognizable structure. There was only gas, gravity, and the slow accumulation of mass. The merger with a galaxy called Gaia Enceladus, roughly 10 to 11 billion years ago, was a pivotal moment. This ancient collision delivered perhaps half the stars in the Milky Way's halo and triggered a burst of star formation that fundamentally altered the galaxy's structure. The thick disk, which had been forming stars steadily for billions of years, received an injection of fresh gas. Star formation rates spiked to record highs, and somewhere in this tumultuous period, the conditions for bar formation began to emerge. Bars form through gravitational instabilities in galactic disks. When a disk becomes sufficiently massive and rotationally supported, when the stars within it are moving fast enough that their collective gravity can amplify small perturbations rather than smooth them out, a bar can spontaneously appear. Small density waves grow into larger ones. Stars begin clustering on elongated orbits. The bar builds itself from the inside out, growing in length and strength as more stars are captured into its gravitational embrace. Computer simulations of galaxy formation show this process in stunning detail. A disk galaxy, stable for billions of years, suddenly develops a spiral disturbance. The disturbance grows, strengthens, and within a few 100 million years, a full bar has formed the galaxy's center. The bar then interacts with the disk, driving spiral arms outward and channeling gas toward the galactic core. The Milky Way's bar likely formed between 8 and 10 billion years ago, based on the ages of stars within it and the structure of the boxy peanut bulge. This makes the bar ancient, older than the Sun, older than Earth, older than any structure in our solar system, yet it is younger than the galaxy as a whole. The Milky Way existed for several billion years before its bar emerged. Once formed, the bar became the central engine of galactic evolution. Its gravitational influence extends far beyond its physical boundaries. The bar does not simply sit at the center of the galaxy, passively rotating. It actively shapes the orbits of stars thousands of light years away. It drives gas inward, feeding star formation in the galactic center. It creates resonances that sculpt the spiral arms and determine where stars can and cannot stably orbit. The mechanism is elegant but powerful. As the bar rotates, its gravitational potential sweeps through the disk like a cosmic lighthouse beam. Stars that happen to orbit at certain frequencies, specific ratios of their orbital period to the bar's rotation period, experience resonant gravitational kicks. These kicks add up over millions of years, gradually changing the star's orbit. Stars can be pushed inward, pulled outward, heated onto more eccentric trajectories, or trapped into stable orbits that follow the bar itself. The most important of these resonances is corrotation, where stars orbit at the same angular velocity as the bar. At this radius, roughly 20,000 light-years from the galactic center in the Milky Way, orbits become particularly complex. Stars can be captured into horseshoe-shaped paths that librate back and forth relative to the bar, never quite catching up and never quite falling behind. Some astronomers have suggested that our own sun may be trapped near or within this corrotation resonance of the spiral arms, which may itself be connected to or influenced by the bar's rotation. The outer Lindblad resonance, farther out in the disk, is where the bar's gravitational influence creates the famous Hercules stream. a group of stars in the solar neighborhood that moves differently from its surroundings. For decades, astronomers debated whether this stream was caused by the bar's outer Lindblad resonance or its corrotation resonance. Recent studies using Gaia data have converged on an answer. The low-pattern speed model, with corrotation around 6 to 7 kiloparsecs, best explains the observations. The bar is rotating more slowly than earlier estimates suggested, and its influence reaches farther into the disk. This slow rotation has profound implications. Bars can lose angular momentum over time through a process called dynamical friction, gravitational interactions with the dark matter halo that surrounds the galaxy. A bar that started rotating quickly billions of years ago may have slowed significantly, transferring its angular momentum to the dark matter and, in the process, altering the structure of both the bar and the halo. Recent work suggests that the Milky Way's bar has indeed been slowing down. As it slows, its resonances sweep outward through the disk, capturing new stars and releasing old ones. The bar is not a static feature. It is evolving, changing, reshaping the galaxy around it on timescales of hundreds of millions to billions of years. The bar is also not alone. Connected to the bar's ends are the spiral arms, the sweeping, curving features that give the Milky Way its classification as a spiral galaxy. These arms are not solid structures, but rather density waves, regions where stars and gas crowd together before drifting apart again. New stars form in the arms because gas is compressed there, triggering the collapse of molecular clouds into stellar nurseries. The relationship between the bar and the spiral arms is complex and not fully understood. In some models, the bar and spiral arms rotate at the same speed, forming a single, coherent structure. In others, they rotate at different speeds, with the arms winding up and regenerating over time. The Milky Way may fall somewhere between these extremes, with the bar and inner spiral arms potentially coupled, but the outer arms behaving more independently. 4 major spiral arms have been identified in the Milky Way: the Scutum Centaurus arm, the Sagittarius arm, the Perseus arm, and the Norma arm. The Sun sits on the inner edge of what is sometimes called the Orion Spur or Orion Arm, a smaller structure between the Sagittarius and Perseus arms. This local arm may itself be a consequence of resonant dynamics driven by the bar, a region where stellar orbits pile up due to gravitational influences from the galactic center. The bar also channels gas. Interstellar hydrogen and molecular clouds do not simply orbit passively around the galactic center. They are funneled inward by the bar's gravitational torques, driven along shock fronts and density enhancements toward the inner galaxy. This gas accumulates in a region called the central molecular zone, a donut-shaped ring of dense molecular clouds surrounding the galactic center. Within this ring, star formation proceeds at rates far higher than in the outer disk. Young massive stars blaze and die within millions of years, seeding the region with heavy elements and creating a cycle of stellar birth and death that has been running for billions of years. What would the bar look like if you could see it? Not from Earth, where dust obscures the view. Not from inside the galaxy, where perspective flattens the structure, but from above, from a vantage point, 1,000,000 light-years north of the galactic plane, looking down on the Milky Way as a whole. You would see, first, the spiral arms, great sweeping curves of stars and dust arcing outward from the galactic center like the arms of a cosmic pinwheel. The arms would not be smooth and continuous, but clumpy and irregular, studded with bright knots of star formation and threaded with dark lanes of obscuring dust. But at the center, cutting across the base of the spiral pattern, you would see the bar, a long linear structure glowing with the ruddy light of billions of old red giant stars. The bar would not be perfectly straight. It would have a slight puffiness, a three-dimensional quality that made it look almost like a cosmic peanut or a squashed football. At its exact center, invisible but palpable, you would sense the presence of Sagittarius A, the dark heart around which all else revolves. The bar would appear to be tilted, one end closer to your hypothetical viewing position than the other. This is its actual orientation, roughly 25 to 30 degrees from our line of sight to the galactic center. The near end points toward the constellation Sagittarius, the far end toward Centaurus. When we look at the Milky Way's center from Earth, we are looking almost, but not quite, along the bar's length. The egg shape would be visible if you tilted your perspective slightly, viewing the bar from a more edge-on angle. The two diagonal arms of the X, composed of stars on vertically extended orbits created by the bar's ancient buckling, would cross at the galactic center. This feature is not visible from Earth's position, but it is there, written into the orbital structures of billions of stars. We live in the age of discovery for the Milky Way's structure. The Gaia spacecraft, launched by the European Space Agency in 2013, has measured the positions and motions of nearly 2 billion stars with unprecedented precision. These data have revolutionized our understanding of the galaxy, revealing structures and streams and remnants of ancient mergers that were completely invisible before. The bar's properties, its length, orientation, pattern speed, and gravitational influence on surrounding stars have been constrained with an accuracy that would have been unimaginable a generation ago. In 2019, astronomers combined Gaia data with infrared observations to directly measure stellar motions in the bar itself for the first time. The results confirm the presence of the characteristic streaming patterns expected for stars orbiting within a bar. Outward motions on the leading edge, inward motions on the trailing edge. A complex choreography of gravitational dynamics playing out across tens of thousands of light years. Future surveys will push even deeper. The Vera C. Rubin Observatory, currently under construction in Chile, will catalog billions of stars across the southern sky, providing complementary data to Gaia's northern coverage. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will observe the galactic bulge with a resolution and depth that may finally settle remaining questions about the bar's detailed structure. And theoretical work continues apace. Supercomputer simulations of galaxy formation now include realistic bars that form, evolve, slow down, and interact with their host galaxies over cosmic time. These simulations serve as laboratories for testing ideas about the Milky Way, allowing astronomers to ask, if the bar had this property, what would we observe? And then comparing the predictions to real data. The bar matters for more than astronomical curiosity. It matters for understanding our place in the universe. The Sun does not orbit a simple symmetric spiral galaxy. It orbits a complex, dynamically active system where gravitational resonances from a massive central bar influence stellar trajectories across thousands of light years. Our position in the galaxy near the outer Lindblad resonance of the bar, possibly within the corrotation zone of the spiral arms, may have shaped the history of our solar system in ways we are only beginning to understand. Some researchers have speculated that the Sun's position near galactic resonances could influence the rate of comet impacts on Earth as gravitational perturbations stir up the Oort cloud of distant icy bodies. Others have suggested that the Sun's relatively quiet neighborhood, protected from the chaotic dynamics of the inner galaxy, may have been necessary for complex life to emerge. These ideas remain speculative, but they highlight a profound truth. The bar is not a distant, abstract structure. It is part of our cosmic context. The bar also matters for understanding galaxies in general. The Milky Way is not unique. Nearly 2/3 of all nearby spiral galaxies have bars. Studying our own bar in detail, mapping its stars, measuring its motions, tracing its gravitational influence, provides insights that can be applied to galaxies across the universe. We are not just studying our home. We are studying a category of objects that populate the cosmos by the billions. Stand outside on a clear summer night, away from city lights, and look towards Sagittarius. The Milky Way arches overhead, a river of soft light bisected by dark lanes of dust. You are seeing the edge of the disk, the compressed glow of 100 billion suns viewed from inside. The center is hidden, obscured by those dark lanes, but it is there, 26,000 light years away, burning with the concentrated light of the bulge and the bar. That bar contains more stars than you could count if you counted one per second for 100 lifetimes. It has been rotating around the galactic center since before the Sun existed. It has shaped the orbits of stars, driven the formation of spiral arms, funneled gas toward the supermassive black hole at its core. It is one of the largest coherent structures in the galaxy, and for most of human history, we did not know it was there. Now we know. The Milky Way is a barred spiral galaxy. The bar is real, it is enormous, it is ancient, and it is home. We are not observers looking in from outside. We are embedded within the structure, participating in its rotation, subject to its gravitational influence. Every orbit the Sun completes around the galactic center, every 230 million year galactic year, the bar is there, wheeling alongside us, a silent companion on a journey measured not in years, but in hundreds of millions of them. The bar does not care about us. It is not aware. It is simply matter, obeying the laws of gravity, following trajectories set in motion billions of years ago. But we can be aware of it. We can measure it, map it, understand it. In that understanding, we find our place, not at the center of the universe, not even at the center of the galaxy, but somewhere in the disk, near a resonance, in the vicinity of a structure so vast that it dwarfs imagination. That is the true scale of the Milky Way's central bar, not just its length in light years or its mass in solar masses, but its meaning, a reminder that the cosmos contains structures on scales that humble human ambition, and that we have only begun to explore our own corner of it. The bar has been there for billions of years. We have known about it for 2 decades. There is so much more to discover. Let us return to the numbers for a moment. Not the abstract figures, the kiloparsecs and pattern speeds that fill academic papers, but the numbers that matter for intuition, the numbers that help you feel the scale. The Milky Way's central bar is approximately 32,000 light-years long. A light-year is the distance light travels in 1 year, about 5.88 trillion miles, or 9.46 trillion kilometers. The bar, therefore, spans roughly 190 quadrillion miles. If you could somehow drive a car at highway speeds, say 70 miles per hour, it would take you about 310 trillion years to traverse the bar from end to end. The universe itself is only 13.8 billion years old. You would need to wait for the universe to age 22,000 times over before completing your road trip. Or consider the stars. Conservative estimates suggest the bar and bulge together contain at least 10 to 20 billion stars. Imagine counting them at 1 star per second. No breaks, no sleep, just relentless counting. 1 billion seconds is approximately 31.7 years. To count 10 billion stars would take 317 years. To count 20 billion would take more than 6 centuries. You could begin counting at the founding of your civilization's first dynasty and still be counting when that civilization had fallen and been replaced by a dozen others. These numbers are not meant to intimidate. They are meant to calibrate. The human brain evolved on African savannas, where the relevant scales were tens of miles and dozens of individuals. We have no native intuition for trillions of miles or billions of stars. The numbers force us to acknowledge that the universe operates on scales that transcend human experience, and that the structures within it are correspondingly grand. The discovery of the bar's true scale has solved some mysteries while creating others. One long-standing puzzle involves the asymmetry of the Milky Way's spiral arms. When astronomers mapped the positions of young stars and star-forming regions in the disk, they found that the Scutum Centaurus arm was significantly more prominent than the Sagittarius arm. Both arms are visible in surveys, but one appears to contain far more stars than the other. This asymmetry makes sense if the bar is tilted relative to our line of sight. The near end of the bar points toward the constellation Sagittarius, but it also intersects with the Scutum Centaurus arm. Stars in this region are piled up, their density enhanced by the bar's gravitational influence. The Sagittarius arm, offset from the bar's main axis, does not receive the same boost. The bar also helps explain the complex velocity structure observed in stars near the Sun. For decades, astronomers have catalogued groups of stars in the solar neighborhood that move together through space, so-called moving groups or stellar streams. The most famous is the Hercules stream, a cluster of stars moving slower than the local average and offset in velocity space from the main concentration of disk stars. What causes the Hercules stream? For years, astronomers debated two hypotheses. Either the stream was produced by the outer Lindblad resonance of a fast-rotating bar, or it was produced by the corrotation resonance of a slow-rotating bar. The two models made different predictions about how the stream should behave at different locations in the galaxy, predictions that could be tested with sufficiently precise data. Gaia provided that data. In papers published between 2019 and 2024, multiple research teams independently confirmed that the slow bar model was correct. The Hercules stream is a consequence of the bar's corrotation resonance sweeping through the solar neighborhood, trapping stars into orbits that produce the observed velocity offset. The bar rotates at approximately 33 to 40 kilometers per second per kiloparsec, slower than many earlier estimates had suggested. But this creates new questions. If the bar is rotating this slowly, its outer Lindblad resonance lies just beyond the Sun's position, at roughly 9 kiloparsecs from the galactic center. This places the Sun in a dynamically interesting region where multiple resonances may overlap and interact. The full implications of this position are still being explored. The bar's influence on gas dynamics is equally profound and equally mysterious. Interstellar gas does not simply orbit the galactic center in smooth circles. It responds to the bar's rotating gravitational potential, piling up along shock fronts and streaming inward along the bar's leading edges. This produces a distinctive signature in radio observations, regions of enhanced gas density offset from the bar's main axis, where molecular clouds accumulate before being funneled toward the center. The central molecular zone, a ring of dense molecular gas surrounding the galactic center, is fed by this process. Gas streaming in from the bar's ends collects here, reaching densities far higher than anywhere else in the galaxy. Stars form in this compressed gas at prodigious rates, perhaps 10 to 20 times faster than in the solar neighborhood. Massive stars blaze through their brief lives and explode as supernovae, enriching the surrounding gas with heavy elements and driving powerful winds that shape the local environment. But the gas does not flow smoothly all the way to the black hole. Most of it stalls at the outer edge of the central molecular zone, held back by some combination of angular momentum, magnetic fields, and turbulent pressure. Only a trickle reaches Sagittarius A itself, which is why our galaxy's supermassive black hole is so dim compared to active galactic nuclei in other galaxies. This stalling has consequences. Gas accumulating in the central molecular zone builds up over hundreds of millions of years, reaching critical densities before triggering bursts of star formation. Some models predict that the Milky Way undergoes periodic starbursts, episodes of dramatically enhanced star formation every 500 million years or so, driven by gas buildup in the inner galaxy. The next such starburst may be 200 million years away. The bar also interacts with objects far beyond the disk. Globular clusters, ancient spherical collections of hundreds of thousands of stars, orbit the Milky Way in a diffuse halo extending far above and below the galactic plane. These clusters formed early in the galaxy's history, some more than 12 billion years ago, and have been orbiting ever since. Their trajectories carry them through the bar's gravitational influence twice per orbit, once on the way in and once on the way out. Each passage leaves a mark. The bar's gravity tugs on the globular clusters, transferring angular momentum and altering their orbits. Over billions of years, these perturbations accumulate. Some clusters have been scattered onto more eccentric paths. Others have been captured into resonant orbits that keep them locked in specific relationships with the bar's rotation. A few may have been disrupted entirely, their stars stripped away and scattered into the galactic halo. The Palomar 5 globular cluster provides a striking example. This ancient cluster, located roughly 75,000 light-years from the galactic center, has developed long tidal tails of stars streaming away from its core. Stellar debris pulled loose by gravitational interactions with the galaxy. Recent simulations suggest that the bar's gravitational torques have played a significant role in shaping these tails, twisting and distorting them in ways that encode information about the bar's mass and rotation rate. By studying the shapes of tidal streams from globular clusters and dwarf galaxies, astronomers can reconstruct the gravitational potential of the Milky Way, including the contribution from the bar. It is galactic archaeology performed not with rocks and bones, but with stars and orbits. The bar's X-shaped bulge deserves special attention, because it represents something remarkable, the frozen aftermath of a catastrophic instability. When the bar first formed, it was relatively thin, a flat, elongated structure confined to the galactic plane. But as it grew in mass and length, it became increasingly susceptible to a particular type of gravitational instability called bar buckling. The physics is similar to what happens when you compress a ruler, push on both ends, and eventually it bows outward, unable to sustain the pressure in a straight configuration. The bar experienced this buckling perhaps 8 billion years ago. The instability grew over hundreds of millions of years, causing the bar to bend vertically, first in one direction, then oscillating back and forth as the system sought a new equilibrium. Stars that had been orbiting in the galactic plane were thrown onto trajectories that carried them thousands of light years above and below the midplane. Eventually, the oscillations damped out, and the bar settled into its current configuration, thicker in the center, with an egg-shaped or peanut-shaped bulge visible from edge-on orientations. The stars that now populate this bulge are not newcomers. They are the same stars that were present in the bar before the buckling. They have simply been redistributed in space, their orbits fundamentally altered by the instability. The buckling may have been a one-time event, or it may have occurred multiple times. Simulations suggest that bars can buckle repeatedly, each episode adding to the vertical thickness of the bulge. Some evidence hints that the Milky Way's bar may have undergone at least 2 buckling events, an initial, strong buckling that created the main X shape, followed by a weaker secondary buckling that further thickened the outer bar. These events left signatures in the distribution of stars. Astronomers have detected subtle asymmetries in the bulge, slight differences between the north and south sides of the galactic plane that may represent the frozen remnants of the most recent buckling episode. The bar is a fossil of its own violent past, preserving in its structure a record of instabilities that occurred billions of years ago. What happens next? The bar will not remain as it is forever. Galactic structures evolve on timescales of hundreds of millions to billions of years, and the bar is no exception. Several processes are already at work, slowly altering the bar's properties. Dynamical friction with the dark matter halo is gradually slowing the bar's rotation. As the bar rotates through the dark matter, the invisible substance that dominates the galaxy's mass, it experiences a gravitational drag that transfers angular momentum from the bar to the halo. This process is slow but inexorable. Over billions of years, the bar will continue to lose angular momentum, its rotation rate decreasing as its resonances sweep outward through the disk. The slowing bar may also be growing. Some simulations suggest that bars can increase in length over time, capturing more stars into elongated orbits as their corrotation radius moves outward. A longer, slower bar would have different resonances, different interactions with the spiral arms, and different effects on the stellar populations of the disk. Meanwhile, the collision with the Andromeda Galaxy looms on the horizon, cosmologically speaking. In approximately 4 to 5 billion years, the Milky Way and Andromeda will collide, merging into a single larger galaxy, sometimes called Milkomeda. This merger will almost certainly destroy the bar. The gravitational perturbations from such a massive collision will scatter stars onto random orbits, erasing the ordered structure that defines the bar today. What emerges after billions of years of post-merger relaxation may look nothing like either parent galaxy. But that is a long time from now. For the foreseeable future, for the next few billion years at least, the bar will continue to rotate at the heart of the Milky Way, shaping orbits, funneling gas, and anchoring the spiral structure that defines our galaxy. There is a peculiar loneliness in contemplating the bar. We have known about it for only 20 years. For the entire span of human history before 2005, every civilization that ever looked at the stars did so in ignorance of this structure. The Babylonians did not know. The Greeks did not know. Newton, Einstein, Hubble, none of them knew that their galaxy harbored a bar of billions of stars at its center. The knowledge is so new that people alive today remember when it was discovered. And yet the bar is ancient. It formed before the Earth existed. It has been rotating at the galactic center for twice as long as our planet has orbited the Sun. Every star we see in the night sky, every point of light visible to the naked eye, has been participating in the bar's gravitational dance since before life emerged on Earth. The contrast is humbling. We are newcomers to a universe of ancient structures. The bar was there before us and will remain after we are gone, unless we find a way to outlast even the merger with Andromeda, which seems unlikely but cannot be ruled out entirely. For now, we are ephemeral observers of a permanent cosmos, briefly aware of structures that will long outlive our species. But awareness matters. The bar does not know it exists. The stars within it follow their orbits blindly, responding to gravity with no understanding of the patterns they create. We are the part of the universe that has learned to see itself, to map the structures, measure the motions, and reconstruct the history of the place where we live. That capacity for understanding is new. It emerged on this planet within the last 100,000 years, reached its current sophistication within the last few decades, and will continue to grow, assuming we do not destroy ourselves first. The bar does not care whether we understand it, but we can care. And in that caring, in that effort to comprehend, we participate in something remarkable, the universe coming to know its own structure. The next time you see the Milky Way, think of the bar. You cannot see it directly. The dust hides it from your eyes, but it is there, behind the darkness, glowing with the accumulated light of tens of billions of ancient suns. It has been rotating for 8 billion years. It has shaped the orbits of stars across the galaxy, driven the spiral arms, funneled gas toward the supermassive black hole at its core. It is one of the largest structures in our cosmic neighborhood, and you are connected to it, bound by gravity, participating in its rotation, subject to its resonances. The bar is not just out there, separate and distant. It is part of the same system that includes your solar system, your planet, your atmosphere, your body. The iron in your blood was forged in stars that orbited the bar billions of years ago. The carbon in your cells passed through stellar nurseries, driven by the bar's gravitational influence. You are made of bar stuff, assembled from atoms that have been cycling through the galaxy since long before the Earth existed. That is the true scale of the Milky Way's central bar. Not just its length in light years, not just its mass in solar masses, but its connection to everything else, to the spiral arms, to the disk, to the halo, to the sun, to the Earth, to you. We did not know about this connection until recently. Now we do. The bar has been waiting for us to notice. To truly grasp the bar's significance, we must understand how unusual it is to know anything about it at all. Consider the challenge. The bar lies at the center of a disk galaxy that we are embedded within, viewing edge-on. Between us and the bar stretches 27,000 light-years of interstellar medium, gas, dust, and countless intervening stars. The dust alone absorbs 99.9% of visible light from the galactic center. We are trying to study an object while swimming in fog so thick that we cannot see our own hands. The astronomers who pierced this fog did so through decades of patient technical development. Radio telescopes, which can detect emission from hydrogen gas, provided the first clues in the mid-20th century. The gas near the galactic center did not move in simple circular orbits, as it would if the center was spherically symmetric. Instead, it showed peculiar streaming motions, inflows and outflows that hinted at non-circular gravitational forces. Then came infrared astronomy. The COBE satellite, launched in 1989 to study the cosmic microwave background, also carried instruments sensitive to infrared light. When astronomers used COBE to image the galactic center, they saw something unexpected. The bulge was not round but boxy, with a distinctly rectangular shape. This was the first strong visual evidence for a bar-like structure. But COBE's resolution was limited. The details remained fuzzy, the structure ambiguous. It took the Spitzer space telescope, with its far superior infrared detectors, to map the bar definitively. Spitzer could resolve individual stars at the galactic center, counting them one by one across different parts of the sky. The asymmetric star counts revealed the bar's tilt. The density profiles revealed its length. The colors of the stars, dominated by old red giants, revealed its age. Each generation of instruments has peeled back another layer of the mystery. Gaia, with its ability to measure stellar motions with micro-arc-second precision, has revealed the bar's dynamical signatures in exquisite detail. We can now watch stars orbiting within the bar, their trajectories tracing out the gravitational potential. We can identify resonances from the patterns of stellar velocities near the Sun. We can constrain the bar's pattern speed from the behavior of moving groups in the solar neighborhood. This progression, from fog-bound ignorance to detailed mapping, took most of a century. And we are not done. Future telescopes will probe deeper, resolve finer details, and answer questions that we have not yet thought to ask. The bar will continue to reveal itself layer by layer as our instruments improve. The scientific community's reaction to the bar's discovery illustrates how science works and how it sometimes fails. Before 2005, many astronomers believed the Milky Way had a bar. Indirect evidence had been accumulating for decades, but the size of the bar remained controversial. Some studies suggested it was relatively small, extending only 10,000 to 15,000 light-years from the galactic center. Others suggested it was much larger. The disagreement stemmed partly from observational uncertainties and partly from the difficulty of defining what constitutes the bar versus the surrounding structures. The Glimpse survey changed the conversation. The asymmetric star counts were so clear, so statistically significant, that they forced a revision of the prevailing models. The bar was bigger than most astronomers had assumed. It was tilted at a steeper angle, and it was unambiguously real, not a subtle feature that required careful statistical extraction, but a dominant structure that leapt out of the data. Some astronomers resisted this conclusion at first. Scientific paradigms do not shift overnight. and years of work had been invested in models with smaller bars, but the evidence accumulated. Other surveys confirmed the glimpse results. Theoretical models were updated. By 2010, the long bar had become the standard picture. Today, it is hard to find a serious astronomer who doubts its existence. This pattern, initial skepticism followed by gradual acceptance as evidence mounts, is how science is supposed to work. The bar's discovery was not a moment of sudden revelation, but a process of accumulating confidence. Each new observation added to the weight of evidence. Each confirmation reduced the space for alternative explanations. Eventually, the conclusion became unavoidable. We live in a barred spiral galaxy, and the bar is enormous. The bar raises questions that extend beyond astronomy into philosophy. What does it mean to know our galaxy? We cannot see the bar directly from where we stand. We infer its existence from indirect evidence, star counts, velocity distributions, gravitational effects on other objects. This inference is extremely reliable, supported by multiple independent lines of evidence that all point to the same conclusion. But it is still an inference. We are constructing a mental model of something we cannot observe directly and calling that model knowledge. This is not unique to the bar, of course. All scientific knowledge works this way. We never observe atoms directly. We infer their existence from spectroscopic signatures and chemical reactions. We never observe black holes directly. We infer them from the behavior of matter nearby. Science is fundamentally a process of inference from evidence, not direct perception. But the bar brings this point home with particular force. Here is a structure containing billions of stars, spanning tens of thousands of light years, present at the center of our own galaxy. And until recently, we did not know it was there. The bar was hiding in plain sight, obscured by dust and made invisible by our position within the disk. How many other structures might be hiding, waiting to be discovered as our instruments improve? The history of astronomy is a history of such surprises. Dark matter, dark energy, exoplanets, gravitational waves. Each represented a feature of the universe that was unknown until the right observations revealed it. The bar belongs to this tradition. It reminds us that the universe is richer, stranger, and more structured than our current understanding encompasses. Consider the bar from the perspective of a civilization on the opposite side of the galaxy. Such a civilization, if it existed, would have a very different view of the Milky Way. From their vantage point, the bar would be tilted in the opposite direction. The near end would point toward different constellations. The dust lanes would obscure different regions of the sky. Their astronomers would face the same fundamental challenge, understanding a structure while embedded within it. But the details of that challenge would differ. Would they discover the bar at roughly the same stage of technological development as we did? Probably. The techniques required, infrared astronomy, precision astrometry, statistical analysis of large stellar samples, are likely universal. Any technological civilization that develops space-based telescopes and computer-aided data analysis will eventually map its galaxy structure. The bar is not a secret that only we can discover. It is a feature of physical reality that any sufficiently advanced observer can detect. This universality is important. It suggests that knowledge of galactic structure is not arbitrary or culturally contingent, but reflects something real about the universe. The bar exists independently of any observer. Its properties, length, mass, rotation rate are objective facts that any competent civilization would eventually measure. We happen to be one such civilization. There may be others scattered throughout the disk, reaching similar conclusions through parallel processes of inquiry. The bar connects us to cosmic time. Think about what it means for the bar to have formed 8 billion years ago. At that time, the sun did not exist. The material that would become our solar system was dispersed through interstellar space, mixed into molecular clouds scattered across the galactic disk. The atoms in your body were part of those clouds: carbon atoms, oxygen atoms, iron atoms, all drifting through space, responding to gravitational forces that included the bars. When the bar buckled, when it developed its X-shaped bulge, some of those atoms were affected. Not directly, your atoms were far from the galactic center, but indirectly, through the cascading effects of the bar's gravitational influence on gas flows and stellar orbits throughout the disk. The bar helped determine where dense clouds formed. It helped determine where stars were born. It helped determine what elements were produced and where they were scattered. The sun formed 4.6 billion years ago, long after the bar had settled into its current configuration. But the bar's influence had already shaped the environment into which the sun was born. The local density of gas, the abundance of heavy elements, the orbital characteristics of the birth cloud, all of these were products of 4 billion years of galactic evolution, during which the bar played a central role. You are not separate from the bar. You are a consequence of it. Your existence depends on a chain of events that stretches back through the formation of the sun, through the enrichment of interstellar gas, through the bar's shaping of galactic structure, all the way to the formation of the bar itself billions of years ago. The bar is part of your ancestry, not in a metaphorical sense, but in a literal, physical sense. The gravitational forces that shaped your galaxy shaped the conditions that eventually produced you. This connection extends forward as well as backward. The bar will continue to influence the galaxy for billions of years. Gas will continue to flow along its gravitational channels. Stars will continue to be born in the central molecular zone. Resonances will continue to shape stellar orbits throughout the disk. Whatever future civilizations emerge in the Milky Way, if any do, will inherit a galaxy structured by the bar's presence. Some of these future beings may be our descendants. If humanity survives and expands beyond Earth, we may eventually spread throughout the galaxy, colonizing other star systems and adapting to environments vastly different from our homeworld. These future humans, or post-humans, or whatever we become, will live in a galaxy still dominated by the bar. They may orbit stars in the bar itself, experiencing night skies blazing with millions of nearby suns. They may study the bar from vantage points that we cannot reach, mapping its structure with instruments we cannot imagine. Or humanity may go extinct, as most species do. In that case, the bar will continue without us, rotating through space, indifferent to our absence. Other species may arise on other planets. Other civilizations may discover the bar anew. Other minds may contemplate its scale and significance. The bar does not need observers to exist. It only needs gravity. We began with a question. What is the true scale of the Milky Way's central bar? The numerical answers are impressive. 32,000 light-years long, tens of billions of stars, 8 billion years old, pattern speed of 33 to 40 kilometers per second per kiloparsec. Corrotation radius of 6 to 7 kiloparsecs, mass comprising roughly a quarter of the galaxy's stellar content. But the true scale is not captured by numbers alone. The true scale includes the bar's gravitational influence on the spiral arms, its shaping of stellar orbits throughout the disk, its funneling of gas toward the galactic center, its role in determining where stars form and where they do not. The true scale includes the bar's history, its formation from gravitational instabilities, its buckling into an X-shaped bulge, its gradual slowing over billions of years. The true scale includes the bar's future, its continued rotation, its eventual destruction in the merger with Andromeda, its replacement by whatever structures emerge from that cosmic collision. And the true scale includes us, our existence within the bar's sphere of influence, our discovery of it after centuries of ignorance, our brief window of awareness before whatever comes next. The bar is enormous, it is ancient, it is central to the structure and evolution of our galaxy, and we have only just begun to understand it. That is the true scale, not just physical dimensions, but the full sweep of meaning that those dimensions imply. A structure so vast that it contains billions of stars, so old that it predates our solar system by billions of years, so influential that it has shaped the orbits of stars from the galactic center to the solar neighborhood. And we, temporary, fragile, curious, have figured out that it exists. The universe does not owe us explanations. The bar did not reveal itself willingly. We had to develop telescopes, launch satellites, analyze data, build models, test hypotheses, and argue with each other for decades before reaching our current understanding. Every piece of knowledge about the bar was hard-won, extracted from a cosmos that does not care whether we understand it. But we do care. That caring, that drive to understand, is what makes us what we are. We are the universe's way of knowing itself, at least in this small corner of space and time. And now that we know about the bar, we cannot unknow it. The bar is part of our picture of reality, woven into our understanding of where we live and how we came to be. Look up at the stars tonight, if you can. Find the Milky Way, that soft band of light across the summer sky. Look towards Sagittarius, toward the hidden center. The bar is there. It has always been there. And now, finally, we know. A final thought before we close. The bar is one structure among many in the cosmos. The universe contains an estimated 2 trillion galaxies, and roughly 2/3 of spiral galaxies have bars. Do the math. There are hundreds of billions of galactic bars scattered throughout the observable universe, each one containing billions of stars, each one rotating through space on timescales of hundreds of millions of years. We happen to live inside one of these bars, or rather, inside a galaxy that contains one. Our bar is not special. It is not the largest, not the oldest, not the most massive. It is simply ours, the one we can study in detail, the one whose stars we can count, whose motions we can measure, whose history we can reconstruct. Every other bar in the universe is beyond our reach, at least for now. We can image them as faint smudges of light in distant galaxies. We can model their probable properties based on what we know about galactic dynamics. But we cannot count their stars or measure their pattern speeds or trace the orbits of individual suns within them. Those bars remain mysteries, known to exist, but not yet understood. Our bar is different. Our bar is comprehensible. We can probe it with instruments that humanity built, analyze it with mathematics that humanity developed, communicate our findings in languages that humanity speaks. The bar is a bridge between the cosmic and the human, a structure of unimaginable scale that we have nevertheless managed to imagine, measure, and describe. That achievement is worth celebrating. Not because the bar cares, not because the universe rewards understanding, but because understanding is what we do. We are the species that asks questions, the species that builds telescopes, the species that refuses to accept ignorance as permanent. The bar has been there for 8 billion years, waiting in the dark. We found it, and now we carry it with us, in our textbooks, in our models, in our minds. The true scale of the Milky Way's central bar is not just astronomical. It is also human, a testament to what curious minds can accomplish when they refuse to stop looking. The bar shines on, indifferent to our gaze. But we are not indifferent. We never will be. That is what it means to be human in a universe of galaxies. To notice, to wonder, to understand,